Hi everyone. Good afternoon, crypto geeks. So let's go ahead and get started. I hope everybody remembers this about a month ago, maybe 5 or 6 weeks ago. I don't remember exactly, but there was a huge vulnerability in Microsoft Windows, which was, and NSA this time was nice enough to let everybody know about it, so vendor could patch it. And why am I bringing up today this thing? Was this an issue with some cryptographic protocol like TLS? No. Was it an issue with some cryptographic algorithm like AES or SHA? No, not really. This was just this vulnerability that could potentially let an attacker do all kinds of bad things was just a result of 1 or 2 stupid coding mistakes. And why is that? So cryptography is hard, right? If anybody disagrees with me, I want to talk to you after this talk. And coding mistakes are bad. We all deal with coding mistakes. And coding mistakes in cryptography are especially bad because virtually all the time they lead to some kind of security issue, like the one we just mentioned. So today we're going to talk about how to exploit some of these coding mistakes, or implementation mistakes, I should say. We're not going to talk about any 0 days. No, not today. There's not going to be any complex math. Everything's going to be pretty basic. We're not going to talk about any about the dark future of cryptography, which is going to be completely broken by quantum computing. And we're not going to break the internet today, which is based on the correctly implemented crypto. All right? So my name is Alexei. I'm a recovering software developer. At some point, I realized that breaking code was more fun than writing code, so I don't write much code anymore. But I do break sometimes. I currently work for a company a few blocks away from here. I'm not actually based in San Francisco, though. I have a couple of industry certs, but there is a fine print on this slide. Oh, here it is. I'm not a cryptographer. So, and I don't even know what the definition of cryptographer is. Is it somebody who invented an algorithm, or I don't know. But anyway, so this is a talk by a non-expert, hopefully for non-experts. But I hope it will be interesting. So a few general recommendations, first of all. We all need to use well-known and secure algorithms, right? We don't use MD5 anymore, or DES. That's clear. And we need to use standard and stable implementations of those algorithms. We don't use some obscure libraries who, and nobody knows where they were written. Very important thing is we need to follow best practices. So if somebody's telling you, if the book says you got to use random IV, there's probably a reason for that, right? And you've heard this advice many, many times. I'm just going to give it to you again. Do not invent your own crypto. The mistakes with cryptographic implementations or code around it can boil down to several categories. First, there could be insufficient entropy, which basically means not enough randomness. And randomness is really important here. Second is algorithm choice. So we don't use the correct algorithm for the purpose. Algorithm-specific considerations are really important because depending on what you're trying to do, there are certain things, certain tweaks that you need to use to get what you need and not to make a mistake. One thing that we often overlook, we tend to focus on secrecy and we forget about integrity. So we hide this message really well, but can anybody tamper with it? And we forget. And the last but not least is you can have a perfect system with very secure keys, modern algorithms, but as long as you don't handle those keys correctly and they leaked, you're broken. Let's talk about a couple of basics first. I hope everybody knows what Exclusiveor is, but if you don't, This is the ultimate crypto weapon for the purpose of this talk, and we'll see why. And there are a few cool properties of this operation. First is anything XOR 0 is the same thing. Something XOR the same thing is 0. And if A XOR B is C, then A XOR C is B, and B XOR C is A. So you can move the parameter on either side of that equal sign. The second basic thing is randomness. There are two big types of random number generators. One is true random number generator, which is non-deterministic and completely unpredictable. And those are normally based on some physical characteristics, maybe ambient temperature or noise or electric current fluctuations or some visual data. And there's no way to predict what the next random number from that generator is going to be. And there are also pseudo-random number generators. And these are completely deterministic. These are algorithms. And they're based on a seed. So you give it the same seed 2 times, and it's going to generate the same sequence of random numbers. And a lot of times we use the combination of both. So we would use the true random for the seed, and then we give it to pseudo-random, and then we get a nice stream that's looking like completely random. Speaking of randomness, a few years ago, some smart guys got fed up with all ransomware being written for Windows, so they decided to create one for Linux. After all, Linux runs a lot of stuff, right? And you could probably monetize something like this really easy. Their problem was they used predictable encryption keys when they were encrypting the data. And researchers found it pretty quickly and released a decryptor which anybody could use to decrypt their data without paying any ransom. And I have a demo. So let's see how it works. So I have a small document which says not all random functions were created equal. And I have my encryptor which encrypted my file with some key that it just created. And actually, it forgot about the key. I don't even have it. But if I look at this document.ransom, it's looking completely like some random binary data. And I have no idea what the key is again and what this document is. But I can use my decryptor script to, if I can type it correctly. And it decrypted that file because in this particular case, it could just get the timestamp of the file modification timestamp and give it to the generator here, and that's it. That's very, very easy. So before I move on, I wanted to mention that all the code that I'm using today is on GitHub, and you'll get a link at the end of this talk, and you'll be able to download it, play with it, do whatever you want. Cool, yeah, so it's a great advice, right? Of course, if you MD5 current time, you're gonna get predictable, random, non-random, whatever. Don't do that. Okay, let's talk about some encryption algorithms. There is a very, very secure, extremely secure, and extremely simple algorithm called Onetime Pad. And it works like this. Suppose you have a message, M, and a key, K. And the encryption would be a simple XOR operation of message with the key. That's it. And decryption is a similar basic operation. You just XOR ciphertext with the key. Here's an example. It's very secure because it was, I think there is a theorem of some kind that says that it's secure, and it was proven. But there is one issue with this algorithm is the key has to be as long as the data. So if you encrypt a gigabyte of data, you got to have a gigabyte long key. And you got to store it somewhere, you got to share it with someone. So it's very impractical. Another issue with this algorithm is in the name. It's called Onetime Pad. But why? So let's see what happens when we encrypt two messages with the same key, message 1 and message 2. Now, if we XOR these two ciphertexts, due to the properties of XOR operation, these two keys will cancel out, and XOR of ciphertext is equal to the XOR of the original plaintext messages. And this is obviously not very good. We cannot reuse keys. And the more messages the more ciphertext we can intercept, the more data we can gather from something like this. So, since the key for Onetime Pad, well, Onetime Pad is impractical because of its key requirement, we use stream ciphers. Stream cipher is using a short key, relatively short, maybe 16 bytes, and it's giving it to a key stream generator function, G, that takes that key as basically as a seed and generates us a stream of pseudo-random data. And our encryption operation is the same as in Onetime Pad. It's just XOR, and decryption is XOR. So it's basically Onetime Pad with a different kind of key. But it's much better because we can manage short keys. But again, we cannot reuse these keys with stream ciphers. Well, there is an asterisk here because in some modern implementations of modern stream ciphers, you can actually reuse the keys because they introduce randomness through some other means. But in its pure implementation and with old algorithms like RC4, this was the case. You cannot reuse keys. So let's see what happens when you reuse the key. I have a visual example. So I have an image of me, cool picture, and another cool picture of a smiley face. These both images are the same dimensions, and I'm going to encrypt them both with the same key using a stream cipher called RC4. And let's see what happens after that. I have my cool script. So I've got to, this is the result of one picture being encrypted, and this is the other picture encrypted. Completely random, right? Can gather any data from here. Well, what if we feed these two images, the encrypted images, to graphics editor? So this graphics editor lets me do a pretty cool thing. I can add, I can overlay the two images as layers, right? And then I can select, let's see if I can make it a little larger. I can select the layer operation, and one of them is XOR. So if I just XOR two layers, it doesn't align really well, but you know, as humans, we can immediately see that something is wrong with this encryption, right? Now, what if we, as attacker, know one of these plain text messages? So let's say we know that one of these messages was that smiley face. So I'm gonna give it to my editor. I'm gonna add that smiley face as another layer, and I'm going to XOR it with that. So having these two layers of seemingly random stuff and a smiley face, I get a picture of me. How cool is that? All right, well, I don't know. So in real world, though, this might not be as simple, right? You might have to do some kind of really smart analysis, but you get the idea. Reusing the key is not a good thing. Okay, let's talk about block ciphers. Unlike stream ciphers that operate with bytes or maybe even bits. Block cipher operates with blocks. So you feed it a block of data. Normally it's maybe 16 bytes. It does a permutation based on the key, and it gives you another block. So that's how the primitive works. But your data is not always as short as the block size, right? In most cases, it's not. So what do we do in this case? The pretty straightforward thing to do is to encrypt each one of the blocks individually, and you get a ciphertext, everything is cool. Well, apparently it's not. And you can guess that the same plain text block, if it's somewhere in the file, will encrypt to the same ciphertext. So by looking at the ciphertext, you can see the patterns, which is not good, as we know that good encryption will result in data that indistinguishable from random noise. And this is not random noise anymore. And let's see how non-random that is. Okay, I have another visual example. This is an image, a screenshot of my title slide. So I'm going to encrypt it. So this script encrypts it twice. One, it's using that ECB mode that we just talked about, and it's also using CBC mode, which we have not discussed yet. So let's see how they differ visually. This is the image encrypted with CBC mode, completely random. And this is the image encrypted with ECB mode, where each block encrypts individually. And although it's not looking exactly like the original image, again, we as humans can immediately see, can immediately get information from here. You know, you can read the text because it's an image. I was cheating, but you know. So, not a good idea. So, what's the CBC mode? So CBC mode introduces randomness, and it doesn't matter whether blocks of plain text are going to repeat. It doesn't really matter because everything is going to look like random after encryption. So the previous ciphertext block is XORed with current plain text before encryption, and that's how that randomness is propagated all the way through the data. With the first block, though, we don't have that previous ciphertext. So what we use is a thing called initialization vector, or IV. And IV is just a random, just some random data, which is equal to the size of the block. And it's not secret. We transmit it with the ciphertext openly. But we just need it for this randomness. The decryption is the opposite operation. So when we decrypt the first block, we first apply that primitive, which decrypts, and then we XOR it with IV. The second block, we decrypt that block and XOR it with C1, and so on. This one we XOR with C2. Some people think that have an idea. Since I already know the key, and whoever is going to decrypt this message later knows the key, why can't I just use the key as IV? I don't have to transmit it, right? Because it's known to both to encryptor and decryptor. I'll just feed it here, and it will definitely introduce randomness. Well, this is not a good idea, because under some assumptions, this kind of stuff is easily broken, and broken to the point that you get the original encryption key, not just original data. So suppose we intercept a message of 3 ciphertext blocks, or maybe more ciphertext blocks, doesn't really matter, because we only use the first one. We use C1, we put it here. Then the next block, we just put all zeros, 16 zeros, or 8 zeros, whatever your cipher is. And the third block, we repeat C1 again. Well, this looks funny, but here's how it works. If we if we assume that we can give this to the decrypter and they'll try to decrypt it and tell us the result, then see what happens. The first block is decrypted and XORed with IV, and IV happens to be the key, so it's XORed with the key. The second block is decrypted to garbage, and we don't care about it. The third block is decrypted and XORed with the previous block, which is all zeros. So on the right side here, we have the result of the decryption of block C1, and here is the same thing, XORed K. So if we now XOR these two plain texts, we get the encryption key. Okay, let's see. I actually have a web application for this. So this application is giving you a session cookie, which is encrypted JSON. And let's suppose the source is open. We can see how it works and what it's doing. But we have no idea about what the encryption key is, right? So here's our encrypted cookie. Let me... So first thing we need to do is feed that cookie to our first step is to build that funny message with zeros in the middle, which are represented by AAA in base 64. Now we give it back to the application. And since it's a session cookie, it expects good stuff from us. I refresh the page and it says, data is invalid, I could not decrypt it, sorry, here is what you gave me, here is what I was able to get. This is the result of the encryption. Great, we say great. Let's just use that. Our second step is this. This script analyzed this message and told us the cookie encryption key is this. Well, let's check it. The server is running on the same machine, obviously. So I can see its session key, which is stored in the file. And of course, I should use something other than cat. And the key is exactly C4, F1, E0, FB, and so on. So we broke the encryption key. All right. So don't use key as IV. Now, not only your message is normally not as short as block, it's normally not, the length of it is normally not a multiple of the block. So what do you do in this case? And because the block cipher only operates on these fixed lengths. In this case, we use padding. So let's say we have 10 bytes we want to encrypt. We cannot just give it to the block cipher. We need to pad it. And padding is just adding the missing number of bytes at the end. In this case, we are missing 6 bytes, and we adding 6 of them. Each one of them is 6, set to 6. That's the convention. Cool, and so this can be encrypted, and this can be later decrypted. And what usually on the decryption side, the program or the implementation of the algorithm checks whether the padding was correct, which may lead to an attack called padding oracle. So if we receive ciphertext and decrypt it, and some people assume that decryption with the wrong key will fail. It's not going to fail. Decrypter will decrypt anything you throw at it. You can throw garbage ciphertext, garbage key. It will produce something. It's just a permutation. But then you check your padding and it's wrong. So in this case, it feels like the right thing to do would be to let user know that the message was corrupted, maybe. So you produce an error message if the padding was wrong. And that leads to an attack called padding oracle. And this attack is I'm not going to explain how it works. It's out of scope of this talk, but basically you modify bit by bit, 256 tries per byte, and you can decrypt the entire message. And although we're not going to go into many details, I have a demo for that, which is really cool, I think. So here's another web application that accepts a message from the user, encrypted message, and it gives me an example here. I don't know what, it's really rude though. I don't have the key, so I cannot decrypt it. Well, if I try to refresh the page, it gives me a new message every time. Actually, the same message is just, it's using random IV, so that's why it's looking different. So if I click here, it's an example. The application accepted that message, told me thank you very much. Okay. What if I try to modify that last byte of that message? It was 2, I'm going to set it to 1. And I sent it, and application gave me an error. Cool, which tells me that I could probably run my pad in Oracle against it. Let's see. Here's my cool exploit. I'm just giving it this exploit script, this URL, and it has no other information. It is just going to go to this server and try to send different things. It's going to try many things, and here is the server log. It's basically accepting hundreds, maybe thousands of requests. But at the end, just in a few seconds, it was able to decrypt the entire message. So this stuff is real, you know. When we read about these things, sometimes we think, you know, yeah, these are theoretical attacks. Well, no, you can actually use them sometimes. So yeah, just wanted to show you what's happening on the back end is just processing the message, is doing the decryption, and then this padding stuff, and then it's just catching the error. I mean, this is like normal way to do things. So if there's errors of some kind, this probably user is giving us garbage and they're not authorized to perform operations. So normal to give an error like this. Well, be careful. Okay, so a few examples so far were based on the fact that our vulnerable applications were not checking the integrity. So like in Pad and Oracle attack, we modified that message bit by bit, and we threw it at the application, and it was trying to decrypt them, which apparently is not a good idea. It should have just rejected, because it should have somehow determined that the message has been modified. Well, yeah, we give it garbage, it processes it. But what about not giving it garbage, but giving it something that you control? So for example, you know that somebody is sending someone a message, send $100 to Alice, and they encrypt it, and all you have is that encrypted thing, the ciphertext. What if you can modify that ciphertext without knowing the key, so when the other person decrypts it, they get what you want the message to be. So instead of sending $100 to Alice, the poor Bob will send $100 to Mallory. Apparently, this is possible, and a simple example of this is with stream cipher using a bit flippant attack. Suppose our message is guessed. It's a string. So our encryption looks like this, remember, right? The attacker will modify this ciphertext that they intercepted by XORing it with original plain text and XORing it with the new message that they want that to be. So when this is decrypted, so when this is decrypted, this is the decryption operation, which expands to this, right? And it further expands to this, and guessed and guessed cancel out, K and GK cancel out, and the resulting message is admin. So it seems like a silly example, but what if this message is used to make access control decision, and this is like your again, session cookie. Let's take a look. Let me refresh this. All right. So in this case, again, we assume that the source is open, we can see it, we just don't know the key. We know that this application is using a stream cipher. In this case, it's Salsa 20, which is a pretty strong modern cipher, which is using a random nonce, so the key reuse is no longer possible. And we know the value of this user cookie, which is printed right here, but we could have guessed it too easily. All right. So I have my bit flipping exploit. I'm giving it that ciphertext. I'm giving it the original value. And I want to give it a new value. If I analyze the code, though, I see that the date parameter is not even used by this application. So I can completely skip it. I'm just going to remove it. It doesn't really matter. I mean, we could keep it, but I'm just going to do it like this. And here's my new encrypted cookie. Again, I mean, my exploit script didn't do anything. It was just XORing stuff. So I'm giving that cookie back to the app. Refresh, and I'm in the admin interface. Well, awesome. Well, stream ciphers are easy sometimes. What about block ciphers? Apparently, bit flipping attack is possible in block ciphers as well, although it might not seem as straightforward. But let's say our message is guessed, and it happens to be in the first block of our encrypted message. So our ciphertext is the encryption of that message, XORed IV. And due to XOR properties, these are true as well. So in this case, what we need to do is to modify the IV. We don't modify the ciphertext, we modify the IV, which is not secret again. It's transmitted along with the ciphertext in open. So we modify it like this. Deja vu, right? We've seen it before. When it's decrypted, that block is XORed with our new IV. And which expands to this. The two IVs cancel out, expands to this, two guesses cancel out, and we get our admin again. All right, let's see if it works. Yeah, so here's our new encrypted cookie. And I need to give it that ciphertext again. I need to give it the original data. Well, actually, in this case, I'm only concerned about the first block. And this happens to be exactly 16 bytes. I'm so lucky today. So I'm going to change this to admin. So it's only modifying IV, which will only going to affect the first block. And when I give it back to the application, I'm the admin again. Well, this was, we got really lucky here, right? But in the real world, you can still do a lot of damage, even if something you try to modify is not exactly in the first block, it's somewhere else. There are ways to do real harm. So integrity is extremely important. In cryptography, we have a thing called authenticated encryption, which means in addition to encrypting the message and hiding it, making it secret, we also authenticate it. So when somebody is trying to decrypt it, they are able to determine whether it has been tampered with or not. So during the encryption, we just provide plain text and the key, and the output of such authenticated encryption will be our ciphertext and some kind of authentication tag. And decryption will validate that authentication tag, and if it sees something weird, like it doesn't match what it calculated, it should just reject the message completely, not even try to decrypt it. Okay. And the last thing for today I want to talk about is storing passwords. We have a couple of rules. Rule number 1, no plain text passwords. Yes? Rule number 2, no decryptable passwords. Right? Because no matter how well you do it, sooner or later your keys are going to be leaked or going to get to the wrong hands, and somebody's going to get the passwords. Rule number 3, no one-way hash, right? I mean, what? I thought everybody was saying that one-way hash is the way to do it. Well, yes, but some people take it literally and they use a hash function. So they use something like SHA-2, which is not a good idea because of its speed. So hash functions are cheap, they're fast, which makes brute force attacks possible. In contrast, key derivation functions, or KDFs, are expensive. They take a lot of time, maybe a lot of memory, or maybe both. And they, when you implement them, when you use them, you want them to be as slow as possible. Like, whatever slowness you can get is the way to go. And I just wanted, I mean, some people, yeah, kind of understand it, but they don't really appreciate how huge the difference is between something like SHA-2 and KDF. So I just wanted to run a very short demo here. This script generates a password hash, and first it does using SHA. And I can use John the Ripper to brute force it using a dictionary. Boom. Took a fraction of a second. My password is Pink Floyd. And John the Ripper tells me that it was able to try 60,000 passwords per second. Not bad. Let's repeat this with pbkdf2 function, which is, by the way, not the best key derivation function these days. But I'm using it here just because it was easy. So let's try to brute force it now. And as you can tell, it's taking much longer now. It ran open threads, eight threads, and okay. Well, it was able to crack it. The password is Pink Floyd, but it was only able to process 85 passwords per second versus 60,000 passwords per second. So, I mean, in this case, it would be really impractical if your password is strong and maybe not in the dictionary file at all, which is what we should all strive for. So, takeaways. If you're a breaker, you need to understand the cryptographic concepts, not just in general terms, but on technical level. You might want to go a little deeper to really understand what's going on. Examining the industry guidelines and understanding them and understanding why they were given at some point in time is very important too. You know, things like, again, not using key as IV, right? There's probably a reason for that. Expand on other people's work. There are some tools. There is my really bad demo software that you can try. If you're a builder, again, you need to understand the concepts and your task. So you need to know what to use when and with what parameters. Because if you use a hammer where you need to use a chainsaw, it's probably not going to work really well. Follow the guidelines. You don't have to understand them. but those FIPS boxes sometimes are useful, although I'm smiling. And learn from other people's mistakes and don't make them again. So for further learning, I just wanted to give you a couple of recommendations. I'm not affiliated with this at all, but there is a really nice course on Coursera called Cryptography 1. It's awesome, awesome, awesome course, highly recommended. And the second one is Crypto 101 online book. It's basically a PDF that you can download and read. It still needs some work, but most of the great stuff is already there. So like I promised, my code is on GitHub. Feel free to fork it, clone it, give it a try. Let me know if it doesn't work. And you can contact me. And thank you very much. And I guess we have time for questions. Any questions? No questions? Online questions?
One question, are the slides on this presentation?
The slides? The question is whether the slides are online. Not right now, but I'll put them up. Thank you. All right, thank you.